All right, so I had a request for a little more help on lesson 128. This is a tough lesson. This is probably as tough as it gets as far as math and formulas and figuring out a schematic and everything. And again, I think the biggest thing I can tell you guys is we have to start breaking these circuits down. A combination circuit is what we're going to be talking about. We have to really start breaking these circuits down, trying to put them into parts that are simple circuits. So that is parallel or series circuits individually. And I'm going to look at these couple problems here. Worksheet 128.4, questions 4 and 5. These are these questions where, hey, you lost a neutral. So what happens to your circuit? We have a multi-wire branch circuit, a shared neutral branch circuit. We lose a neutral. What happens? This is a fairly common service call. Now, never are you going to calculate the voltages. You just know that everything has gone haywire. Why did it happen? Most people know, oh, you lost a neutral. But this, I think, really explains why. So I think the book maybe takes this a little too far, but here it is nonetheless. So let's really break this down. Excuse me. So let's just kind of look at this whole. Both these questions relate to the same circuit. So I've kind of redrawn this circuit in a more direct way we can kind of understand. So we have 4 equal loads here. We have 3 connected to this phase. We have 1 connected to this phase. And then we have a shared neutral going back. So what's the current flow look like in that circuit? Normally should look like that. So in this case, both circuits have 120 volts applied to all the loads, all the elements. Everything's great, running good. But now, for whatever reason, we lose the neutral. We have an open splice. Whatever happens, we lose this neutral. So now, instead of a multi-wire branch circuit, we've just created a combination circuit, right? So we have this section here. These 3 are connected in parallel with each other, whereas now this section and this one load are connected in series, right? So again, we have to, let's break this down and simplify. So can we look at any part of the circuit and make it a simple circuit by itself? And the answer here is we can. Here's 3 loads in parallel. So let's kind of isolate that and just look at that and just try to do some calculations on this. So the first thing, I'm going to bring up this table again. I really think this is a great way to solve any of these types of problems. So they told us right off the bat that each of these has 60 ohms of resistance. So we know that we can fill that in for all 3, F, G, and H. Usually we can fill in the voltage. In this case, we can't because we don't know what effect this element's going to have on our voltage. So really the only thing we can do is calculate our total resistance. And this is one spot where we can't get around this big, nasty parallel circuit resistance formula. But I'll save you the trouble here. If we go ahead and calculate that out, we get 20 ohms. Okay, pretty simple. So we can put that in for total resistance. So, at this point, from a resistance point of view, we've kind of reduced this. Let's consider this to be now one element. We'll call it F, G, and H with a total resistance of 20. Right, so we've simplified this down sort of in our imagination as one load now. So let's bring the rest of the circuit back in. So if we assume this now is one load from a resistance point of view, we can now see we basically have a simple series circuit here at this point. So let's get this guy out of our way. And now we're going to start a new chart for just this series circuit now, right? So we have a column for total, we have a column for the F, G, and H load, we have a column for the J load. So all of our total values here are going to actually be the same as these F, G, H values here. So we know 20 was total resistance, we can throw 20 down for the resistance of F, G, H. We know from what they told us that J has a resistance of 60. Do we know anything else? We actually do in this case. We said this was a 240 volt system here, so we know that there's 240 volts applied to this entire circuit here, right? We can also determine the ohms, the total ohms, using our ohms rule for a series circuit. Ohms is additive. 20 plus 60 gives us 80. So now we're really getting some things filled in here. What else can we do? We can go ahead and use Ohm's law at this point and fill in this whole entire column. if we do amps first, what do we know about, we're using Ohm's law to determine 3 amps. What do we know about amps in a series circuit is it's equal all throughout, so we can actually carry that through all columns here. So like I said, this column is effectively exactly the same as this column. So we can take that 3 amps and throw that up here as well. So that's kind of filling in this chart pretty nicely. That's a good thing. We can then use our Ohm's law with these 2 values and these 2 values to calculate our voltage for both these columns. Once again, I can throw this 60 up here. These columns are effectively the same, right? Okay, so what do we want to do next? Well, let's just kind of use some Ohm's law here. We can calculate our wattages. So now we've kind of got the entire circuit values all figured out, right? This is everything for the total circuit. Once again, we can take this wattage, throw it in up here, right? So we've got this all figured. What are we going to do to finish this out? Well, let's kind of first move this out of the way, but let's isolate this and bring it and sort of separate it again into its original parallel circuit. So what do we know about volts in a parallel circuit? We know that those are equal throughout, right? So we can go ahead and throw that across. Now we really just have to do some Ohm's law to figure out the rest of these values. So, let's go ahead and calculate our amps here using Ohm's law. And volts divided by ohms in this case is going to be 1. And then same thing for watts. Let's calculate our wattages. We can do volts times amps, 60 times 1. That'll give you 60 there as well. So now we've figured out all the values for each individual element for this total portion of the circuit, which is this column. Let's bring back the rest of the circuit here in its original form. So we figured out all the values for this J element, which is this column. And then we figured out the total for the entire circuit, which is this column. Once again, this column and this column are identical. They're the same thing. So if we go back to our questions here, first question asks us, the current through line 1 with the neutral open is blank amp. So the current through this section, the current through this line right here. So that would actually be the total current for this whole guy right here. So we can come back and look at amps would be 3 in this case. So your answer on that question should be 3. Next question, and I disagree with what the LMS says is the correct answer. So the question here is the voltmeter shown in the circuit should indicate blank volts. Actually, I'm sorry, I don't disagree. Actually, I totally agree. I looked at that wrong. So they're at basically, what should the voltage on this voltmeter read? So we put voltmeter leads here and here. What should that voltage be? So if we come back here, they're basically asking us what's the voltage across F. And we can find that easily enough by going to our F column, going to volts. We can say, hey, look at that, it's 60. Right? So our answer in that case should now be 60. So again, that's a very complicated calculation. You can see why everything kind of goes crazy. I mean, this lamp gets 180 volts applied. These only get 60 volts applied. So these are now halfway dimmed. This one just blew up. And in fact, if these were incandescent lamps, we just blew this up. Now the circuit's open. Now nothing works. So I mean, you can just see the amount of trouble that's going to cause. But that's a very complicated calculation. My advice is, A, simplify circuits. Go back and look like we did here. Where can we sort of isolate simple circuits and get it back to parallel and series? And you have to start by finding all the resistances you can and kind of sort of simplifying until you have it down to one simple circuit, one parallel or one series circuit. And then you almost got to kind of expand it back out again when you find the other values. I don't want you to stress on this too much. You guys do have some equations you're going to have to do. You have some problems you got to figure out. But beyond this, I think the book really expands this pretty far, probably a lot further than most electricians need to. But nonetheless, that's the technique. There's not really a step-by-step because everyone is so different. But hopefully you guys find this as a help.